Hello again. What we're going to look at today, okay, is internal energy. Okay. Before we start, I just want to make clear, guys, what we're doing here has got a few reasons behind it. Okay. The first thing, this video should help you to understand the science better. You should be following along, making notes, okay, and you should come out with a nice diagram, okay, a mind map almost of the ideas that we're going through. Okay, so that should help you, firstly, to remember it better. Secondly, to link all the information together neatly. And thirdly, it means that what you should also get at the end of it is a revision aid. That this time next year, when you're actually doing your revising for your GCSEs, then you have this to come back to, and it should just quite easily help you to remember what you've already learned. So please make the notes as we go along. All right, so internal energy. Internal just means inside. So we're talking about the energy that is inside a substance. Okay, so let's have a think about where that energy might be. So we've looked already in a previous topic about different types of energy. The internal energy, okay, is the total of the kinetic energy and of the potential energies of the different particles. Okay, I'll come back to that in a moment. So let's have a think about an ice cube. Okay, so let's draw our little ice cubes. That'll do like that. Obviously, an ice cube is chilly, so we'll just shade that in a little bit of blue. Okay, it looks a bit like a loaf of bread, so let's just make it look a bit less like a loaf of bread. Okay, now if we zoomed in on this, what we'd see is we'd see a load of different water molecules that are arranged, okay, in a regular arrangement. It's not quite what you'll have seen. Remember our little picture of a little picture of a solid looks a bit different to this because we're now looking at a very specific substance, and that specific substance will have a specific shape, a specific way all of the little particles are arranged. So here's our water, and you might recognise, I hope you do recognise in fact, that this is a very similar kind of shape to the shape of diamond. Okay, so ice in fact has the same structural arrangement as diamond. These orange, these red, they're oxygen, and the white ones are hydrogen. Now, as we know, in a solid, the particles are vibrating a little bit, okay? And so that's got the kinetic energy, okay? So there's the kinetic energy, Ke, okay? And there's also potential energy that is to do with the arrangement where the particles are in relation to each other. It is not, and I'll make this really clear, not GPE. Okay, it's not that. So they're in a fixed position. Okay, but there's other potential energies there that we don't really need to go into detail about, but you just need to know that that's where the internal energy is. It's the vibrations, the kinetic energy here. In this case, it's vibrations because it is a solid, and it's the potential energy due to their various positions, okay, in relation to each other. And that is what internal energy is. Total of kinetic energy and potential energies. Now, let me just go into a little bit further detail. If I was to take my ice cube and put it in a car, that's my actual car, okay, and drive off, that does not add to the kinetic energy here. Okay, so we do not include, cross that out in big red, we do not include the kinetic energy of the whole substance. So me taking it out for a walk or going in a car, that doesn't count. It's only the kinetic energy of those particles vibrating. Okay, and we know that these guys have got energy, so that's where that whole total internal energy is. Okay, so now that we know what internal energy is, let's take a little bit more of a comparison between our solids, our liquids and our gases. So let's have a look in a solid in general. Okay, and we're going to take different examples and they're all going to be at the same temperature. Okay, so if we drew a solid diagram, there we go. Right, so my first mistake there. It's a bad Steve point. Okay, they need to be touching. So I should be a bit more careful about, no, it's not touching there. I'm hoping that you'll forgive me about this one. It looks a bit like a Lego brick, doesn't it? Anyway, so that's our solid arrangement. We've got these solid particles. Let's give them a bit of colour, shall we? There we go. And at room temperature, okay, those particles are vibrating, as we've covered. Okay. Let's make that clear. Okay, just a little bit of movement. Okay. So these guys are vibrating. Okay. Now that is our kinetic energy. If I was to apply heat to this, they would vibrate more. Okay, until there comes a point where we've heated them so much that the kinetic energy, or the energy that they've got, overcomes the bonds. Okay, and I'll signify those bonds in a purple colour, like that. Okay, so we'll just call that, that's not quite what it looks like, but we'll put those on there so that we know that the bonds hold the particles in a fixed position, and that only allows them to vibrate. If I heat them up, they're going to vibrate more. Eventually, what's going to happen is that they'll turn into a liquid, okay? Because those bonds will be overcome by the we'll give it so much kinetic energy that those bonds will break. Now, so if I had the example of this is iron, okay, at room temperature it's a solid. Room temperature, it's a solid, okay. So this has got, these bonds are pretty strong because even at the room temperature, which you may not think is particularly hot, but it's, you know, nearly 300 degrees hotter than than deep space, which is at almost absolute zero. Okay, so those bonds are pretty strong because they're holding the iron together. If again I now draw a liquid, okay, oops, that is not a super box, but not to worry. My liquid particles are now jumbled up. I've done 6. I'm going to make these water, okay, because we know that water at room temperature is a liquid. Okay, so where's my pen pencil. There it is. Right. Liquid. So these are now able to move past each other, okay? So particles can move now, right? And they can move because they're not rigidly held, okay? And it's got weak attractions. And those weak attractions means that the particles are not held rigidly, but they are but they're still attracted to each other. So they're strong enough that the particles can't fly off. Cannot fly off. Okay, but they're not strong enough to hold these particles in a rigid formation. So I'll just draw some little. Can't really see that one. Dark green. Okay, so there's some weak attractions there. Just like that. Okay, so again, if we're going to heat that up, then eventually we'll give that enough energy that these particles will be able to fly off. Okay, but at room temperature here, water at room temperature equals a liquid. Okay, so we've got those attractions. Okay, the attractions are not particularly strong. They can't hold this in a rigid arrangement, but they do stop the particles actually just from flying off. Okay, and now, finally, I'm going to do gas. Now, I'm going to have to zoom out a little bit here, so my particles are going to be quite small. Okay. 5, 6. I try really hard not to draw them in a neat arrangement, and it never quite works out. So, let's have these gas particles orange. Okay, so these gas particles are now, you can see they're dispersed. Okay, they're separate, they're whizzing about all over the place, as we like to say. So let's give them a bit of... those two are going to crash. Okay, so these guys are zooming about all over the place. Okay, so the particles, the attraction is so weak that it's insignificant. Is insignificant, which you should know just means it might as well not be there. Okay, so the particles are not held together at all. Okay, and they are flying about. Okay, and this we'll call oxygen. Okay, and we know that at room temperature, this is a gas. So these have all got the same amount, roughly speaking, of internal energy because they're at the same temperature. Okay, but you can see that the attractions are different because these bonds are really strong, so they're holding everything in a really fixed position and they are unable to move. In a liquid, the attraction is weaker, okay, so the particles can't fly off. And in this gas, okay, the attraction is so weak that it's insignificant, so they're not held together and the particles can just go flying off, right? And this is, we know this because they're all at the same temperature. So let's think about a different idea. Okay, we've now here, you can see I've got a cup of ice, okay? That is cold. If I was to take the temperature here, which I can do, so I've got a thermometer. Okay, so if I was going to take the temperature here, then that would be at around about 0. Okay, you can see it's in the process of melting. Okay, there's some water at the bottom there, and it's gone a bit frosty, right? But that, as you can see, that's solid, that's in a rigid formation, okay? But I'm raising the amount of internal energy, Okay, so I'll just pop that there. So what we're looking at now is that we're going to go from a solid to a liquid, but of the same substance. And in order to do that, we need to change the amount of energy. And the amount of energy will then turn it, as you can see, this is now melted, okay, and turned into liquid water. So all the particles are able to flow about, they're able to move. If I can put my finger in it and the water will move around the outside of my finger, okay, because the particles are now separate, okay, they've got a weak attraction, okay, but they can't, the particles can't just fly off. All right, the last thing that I need to tell you about is we can, in order to, whilst we've got our solid, if we heat our solid up, we can calculate the amount of energy needed to raise the temperature of this by a degree C. If some of you, this might be ringing some bells, but if we use the equation that energy equals mass times specific heat capacity times change in temperature, okay, times temperature change, then that can tell us how much energy we need to put in order just to raise the temperature. So we'll write that out again in shorthand. Delta E, which is the energy change, equals the mass of the substance that we're heating, M. It's another bad Steve point for me there. It's not going well today, guys. Oh. M. C, okay, is the specific heat capacity, which is a constant, which is why it has been given the letter C. E equals MC delta. Now, theta, or you could see that as a T, a capital T sometimes, but at the moment we're using theta. Okay, so mass is kg, kilograms. Temperature changes degree C or Kelvin, okay, because 1 degree C is equal to 1 Kelvin, and specific heat capacity is joules per kilogram per degree C. Okay, so that's all I've got for you today, guys. Remember, internal energy is the sum, it's the total of the kinetic energy and all of the potential energy due to relative positions, but not GPE. And the kinetic energy does not include the kinetic energy applied to the whole substance. So if I'm moving it, for example, that is not included. Solids at room temperature have got stronger bonds than liquids, which have got stronger attractions than gases, which have virtually they have insignificant attraction. Okay, in order to change a specific substance, we just need to apply heat till the kinetic energy increases so much that it overcomes these bonds and allows the particles to move around. And then similarly, if we heat our liquid up, then it will overcome these attractions and fly off and turning into a gas. All right, guys, keep yourselves well, and I'll see you soon.